Alright, let's now take a look at an example, and we're going to look at the continuous case, meaning we're going to deal with continuous random variables. You should know what a random variable is. If not, go and watch my statistics refresher. So in this case we will have a binary classifier. We have two classes. We have an A class for adults and a C class for child. And we will look at two features. We will look at height and weight of that particular person. So two classes, two features. This means we have four conditional probabilities. And these are the probabilities. Given that the person is adult, what's the probability of x1? And given the person is adult, what's the probability of the x2? And we know in naive Bayes, we can just multiply these probabilities. Yeah? So now let's take a look on the graph of what we're actually doing. The first time we do, so these are the points. We have 12 children and 2 adults. And we can already calculate the prior. This is something we need to do when we do naive Bayes. Is the probability of an adult and the probability of a child. It will be divided by 16 because we have 16 points, and for adults it's 4 out of 16, and for children 12 out of 16. So that's 1 out of 4, and that's 3 out of 4. Okay, so these are the priors. So the next thing we need to do, we need to decide on a model. Yeah, and this is of course what the data scientists need to do. And it's quite important because if your model is not correct, the chances are your classifier won't be too good. Yeah? Since we're dealing with a continuous distribution, it's quite obvious that we're going to look at a Gaussian here. A Gaussian distribution with parameters mu and sigma squared. Okay? We basically have 4 Gaussian distributions. Yeah, 1, 2, 3, 4. Okay? So let's draw them up. Yeah? Let's start with the red points. We're going to project them on this axis and on this axis. So here we have 2 points. Here we have 1, and here we have 1. Okay, so I can draw a Gaussian that will look like this a little bit. And we do the same here. I have 2 points here. I get 1 point here and 1 point here. So probably a little bit like that. So these are already 2 of the Gaussians. Now we're gonna take a look at the children. Here's 1 here, 1 here, 2 here, then 4, 1, 2, 3, 4, then another 3, 1, 2, 3, and then another 1. Yeah, so here we have our Gaussian, okay, for the children. And the same on this side is 1, here I have 2, another 2, another 3 here, 2 and 2. So it will be something like this. So we have 4 Gaussian distributions. And the Gaussian distributions are going to allow us to calculate the probability of an adult given X as well as the probability of a child given X. Yeah? Probability of adult of X given an adult, it's the probability of height given an adult times the probability of weight given an adult. And here is the same, height given a child times the probability of weight given a child. Yeah? So from here on we can calculate the probability that that you are an adult given the x, yeah? So we use base here, that's px given a times pa divided by, a factor, a normalization factor, which I'm not going to write down. I'm not going to make any calculations, I'm just going to show you how to calculate. And a child given x is exactly the same. X given child times p of a child divided by norm. Yeah? And this PC, PA, this is exactly what we calculated here. Yeah? So this is basically going to be your end result. But how are we now gonna be able to visualize? Yeah? Well, these Gaussians here, if you look at them together, these are actually 3D Gaussians. So you have one 3D Gaussians for the children and one 3D Gaussians for adults. Yeah? So you're gonna look on top of these Gaussians, then you're gonna get some spheres, ellipses. Yeah? So I will draw them. Yeah, you're gonna get some of these, yeah. That's one distribution for the children, and for adults you're gonna have something similar. Huh? Okay. Now, what is very important to understand is that number one, what if we would use a perceptron to separate these data? Well, you would not be able to. And because of this game breaker here, this party breaker, red one here, prevents us from finding a line that separates black and red. So the perceptron will not converge. Yeah. So what we do in naive Bayes is not, we don't have a hyperplane that separates the positive class from the negative class. Yeah. But instead we have a hyperplane that divides two distributions. Yeah. So you find a hyperplane that divides two distributions, and that means that the data doesn't have to be linearly separable for naive Bayes to work. So that is the big difference. Yeah? So in naive Bayes, yeah, you will find a hyperplane that best separates distributions. Okay, so this is the most important conclusion. So if you take a point x test here, for example, x test, so what you're basically gonna do is you're gonna calculate these two probabilities. Yeah, so the chance that it's an adult given x test, and the chance that it's a child given x test, and whatever is the highest probability, that will define the class, adult or child.